Hello guys, you're welcome once more to NEPH, your YouTube channel where we solve problems on physics. And today we are going to look at the second series on measurements in physics. So measurement is very, very vital as far as physics is concerned. As far as we talk about the world of engineering, science, construction, building, measurement is very, very important, okay? Because if you don't measure things accurately, it can lead to what severe what damage. Okay, imagine if you are, building a building or constructing a bridge, and just a slight mistake of 0.01 millimeter like this, can cause a severe damage. All right, so you want to be good with measuring. So the question we have on the board is, what is the accuracy of a typical micrometer screw gauge? Micro, okay, it means it can measure very small dimensions. Okay, it can measure the diameters of wire. It can measure a pendulum bulb. Let's say this is a pendulum bulb. Okay, pendulum bulb. It can also measure what? A piece of what? Paper. So the micrometer screw gauge is more precise, okay, in measurement as compared to what? Your meter rule and your what? Your vernier what? Caliper. So that's one thing to take note. So now for your micrometer screw gauge, it can measure as minute as. Now we have, if you look at it, we have the main scale. For instance, let's say the main scale is reading a 7.50 millimeter. Then you come to the vernier scale. The vernier scale has what? 50 divisions, okay? Such that if we look at this length, it is 0.5 millimeter divided by what? 50 divisions. And if we divide this, we are going to get 0.01 millimeter. So it is so exact that it can measure as minute as this. So let's say, for instance, we move from 0. What? Let's say we have 1, we have 2, 3, and here is 25. Now this 25 there means what? Plus the vernier scale means 0.25 millimeter. So if we sum this, you are going to get 7. What? We have 7.5 millimeter. So this gives the exactness of the micrometer screw gauge in measurement. It can measure as minute, as micro as this. So if we look at the board, the right answer to this problem is this. Now, if it is for a vernier scale, we'll be looking at the accuracy to be this. But for a micrometer screw gauge, it is more exact compared to the meter rule and vernier caliper, so it can measure up to this. So that gives us the solution to this problem. Yes, let's look at the second question in this second series. Okay, the question says the term parallax error is associated with which of the following terms? So what we are looking at here is parallax error. In measurements, you want to be very, very careful of your view, because if you are not very careful, you make mistakes or your reading will become incorrect. For instance, when we say parallax error, it's associated with scales and meter rule. Okay. Now, if for instance you have a meter rule, okay, and you are looking at a reading here 5 cm, so you want to look at it, directly in line. You don't want to look at it from side. All right. If you look at it from sideways, okay, you are going to get what? Incorrect what? Reading. So that is what is called parallax error. The error that occurs due to what? An observer's eye is not directly in line with what is scale. So when you are looking at your scale or meter, you want to look at it direct, not from the side. Okay? So now let's look at the options to pick the correct answer. Now, incorrect stopwatch. Okay, it has nothing to do with stopwatch. Errors in counting oscillations. Okay, what we mean by oscillation is when something goes to and fro, when something is swinging. Okay, so it has nothing to do with this. Okay, All right, the next one here again is fluctuations in electric current. It has nothing to do with electricity. What about this? Misalignment, okay, of the eye. Yeah, misalignment of the eye when reading a scale or meter rule. So this is the correct option, B. All right. For question number 3, right, let's look at the question. It says, which quantity is dimensionless? All right. Now, when we say dimensionless, it means it has what? No unit. Okay, so you have to take note. It means it has no unit. Now, let's check each and every one of the quantities we have on the board to see which of them has no unit. Now, for density, the formula is what? Mass divided by what? Volume. Mass has a unit which is what? Kilogram, and volume is what? Meter what? Cube. So the unit of what? Density is what? Kilogram per what? Meter what? Cube. For energy, we have it as what? Joules. Okay? Whether kinetic energy or potential energy. All right? Now for force, the formula for force is mass times what? Acceleration. Mass, the unit is what? Kilogram. Whereas for acceleration, we have meter per second what? Square. But this, we can simply call it as what? Newton. So the unit of force is Newton. But for strain means the ratio of what? Change in length, okay, divided by what? The original length. Let's say if I have this as the length, okay, let's call this L1 as what? Let's say 4 centimeters. And this length happens to maybe expand, okay, so say L2, which is what? Say 6 what? Centimeters. We can calculate the strain here. How do we do that? We can say L2 minus L1, so 6 centimeter minus 4 centimeter, divided by what? The original length, which is 4 centimeter. So 6 centimeter minus 4 centimeter is 2 centimeter, divided by 4 centimeter. Now this will cancel this. Okay? So if we divide this is 1 over 2. 1 over 2 means 0.5. So for strain has no what? Unit. As you can see from this calculation, we have 0.5. So what that means is strain is what? A dimensionless what? Quantity. So our correct answer to this question is what B. Let's look at the fourth question in this series. So we have, what is the estimated what? Uncertainty in the measurement of this. Okay. So the first thing we want to understand is, what do we mean by what? Estimated uncertainty. It has to do with the range within which what a value lies. Okay. Now, what I mean by the range within which a value lies is this. You in physics, you may take a measurement, okay, and let's say because you are using a meter rule, okay, for you to be able to measure, a very small centimeter, it is such that it is not so clear. Let's say this is a meter rule. Okay, we have your calibrations like this. Let's say this is 5, and you have some points here. Now, let's say this is the exact point. Okay, so you have, let's say this is 5. Okay, 5.25. Okay, at this point. Now, plus or minus. Okay, in fact, let's use 4. Let's use the 4. So now, this point can be in between what? Two what? Scales. So it is that which we now use as what? A range. We can say plus or minus 0.05 centimeters. So what this is trying to tell us is this. Now, if we add 0.05 to this, we are going to get what? 4.30. We will subtract this from this. We are going to get what? 4.20 centimeters. So this range, okay, it means this range is whatever it is we have measured that this lies within. So now the estimated uncertainty actually is this value. So to this problem, the estimated uncertainty is this, which gives us this range of values. So this gives us the correct option to this problem. So guys, now let's look at the last or the fifth question in this series to end the series. All right, so the question is on what is the purpose of what zero error? Okay, zero error correction in measuring instruments. So what do we mean by zero error correction? Zero error correction has to do with when your meter rule or your scale, okay, is damaged at both ends of the what? The scale. And that may lead to what? Incorrect what? Measurement. Because you don't have what? Your meter rule does not what? Read zero. For instance, let's say I have a meter rule like this, okay? So this is 0 down to 30 centimeters. Let's say this end have worn out, okay? If these ends are worn out, so you see that you cannot start your measurement from this. For instance, let's say we want to measure, we can start with what? From 2 centimeters down to a 0.8 centimeter. So let's say what we want to measure is from this point down to this point, okay? Let's say this is a block that we're measuring. So the accurate measurement or the correct measurement will be 8 centimeters minus what? 2 centimeters. So our length here is 6 centimeters. So you don't want to start with what? 0 because this part is worn out. So the essence of what? Zero error correction in measuring instruments is such that you want to improve your accuracy, okay, in your measurement by eliminating, this is the initial what? Offset, okay? So now let's look at the options to know which one is the correct answer. The first one says to improve accuracy by eliminating initial offset. So this is the correct answer. Okay. The second one says to measure zero quantities. No, there are no zero quantities to measure. To calibrate the instrument for different units. No, we are not calibrating it. Now, to ensure readings are always positive. No. All right. So this is the best answer to improve the accuracy because you can't measure with this worn out spot. All right. So that ends this series. Make sure you hit the like button, subscribe to this YouTube channel. I'll see you guys in my next series. All right. Don't forget to share this video to somebody. All right. See you. Bye.